So now we are ready to do something even more. So we have seen in FreeCAD that we can use that and use also the calculus and do some FEM simulations. Now we're gonna do something like an extension, or you may see that as an alternative as well. What is that? We're going to use FEniCS. So in order to use FEniCS, you should already have some basic understanding of that. If you don't have that, so just recap what we have already discussed. And now what we want to do is now the implementation at geometry in FreeCAD. So that means we can have a really sophisticated geometry. And then using this geometry in order to do an FEM simulation, but this time using FEniCS. Okay, let me start with that. Of course, first we need a geometry, right, in FreeCAD. So I'm going to do something really basic in order to have a good understanding of what's going on. Let me go to the part design. It's been a while. So I'm gonna make a create body and a sketch. Of course, I need to choose a sketch. So what I have in mind is something like a beam. Okay. So let me have a beam, which is, the dimensions are not so interesting. So I'm gonna make something like that, and then let's close and create a path. So this is more or less a beam. It is a little bit boring, I know that, but we can do a bit fancy. So I can make some holes on it, right? In order to make it more fancy, let's make some holes on it, and I'm gonna punch a couple of holes on it in order to have something more at least interesting looking. So of course they don't have to be like the same size, one small, one big. It doesn't look like a technical application, but why not? Let's be somehow creative. Okay. All right, so if I say closed, now I can have a hole and it is going to be like through, or I can say pocket and make like only the halfway through. I'm gonna make holes, so it's gonna be like all of them through. So, okay, that looks like this. It's like a punch specimen. I don't know why, but it looks cool. So let's say, okay, so that's the model, that's the geometry what we have. Of course, for any FEM simulation, what we need to have is a mesh, but all the rest, the boundary conditions and the material equations and so on, we are going to do in FEniCS. Okay, that's the key idea here. So I need to have the mesh, and that's it. In order to do so, I'm going to open the workbench of FEM, and selecting the body, I can now use the meshing possibility. So I'm going to use again the mesh gmesh. This is key. So here the element order, because we are going to create a mesh, and then we're going to transfer this mesh to FEniCS, and the rest will be just Python code. In order to have this transfer possibility, we only want to have the nodes and where they are, the elements and so on. So therefore, we need to have first order element. After that, if we have it in FEniCS, then we are free to choose if we want to have first order or second order. That's up to us. But in order to make the mesh compatible or transferring the mesh to FEniCS, we have to have here first. So that doesn't matter. So it's going to be, of course, 3-dimensional. I can say apply. Okay. So I'm going to redo the mesh later on better. So that's okay. So what is important is, of course, we want to be able to do some boundary conditions, right? So the boundary conditions, I can choose here the surfaces, and then later on in FEniCS, I can find out what I have chosen here. So in order to do that, I'm going to use mesh group. Okay, so here I'm choosing the mesh. After I have chosen the mesh, I go on top to the mesh group, and here FEM mesh group. If I click that, so now there are a couple of different possibilities. First of all, I'm going to use here label. Okay, so that's for the mesh export. This is key because I'm going to use these labels later on in coding in order to distinguish which surface is which surface. So I'm going to use label. First, I want to have a solid. Okay, that's the whole body. The whole body is a solid. So here first I need to choose add, and after choosing add I can choose the body. Okay, so the other way around is not working. I cannot choose first the body and then say add. It's not possible. First I need to choose add and then choose the body. So then you see immediately here, okay, that's the solid it's just an internal name Freecad is giving us. It's not important. So I'm gonna say okay. So now we can also have a double check. By the way, this is gray, you see? I can now double check. So there's a mesh group. So, and the mesh group has some properties, and one of them is label, because I have selected, I can double click on it, comes again the same, because I have selected label here, all right? So if I click on that, this label, I can go in by just clicking in and change it. I'm gonna give a name, which is important for me to identify later on in FEniCS. So a name that I know, that's what I want to have. I'm just gonna use body, okay? So, by the way, this is grayed out, okay? So that's important, so that this is grayed. So, because that means it is not possible to do something further, or it actually indicates that this body is what we have defined. We already said where is the body, but this is not a definition, or is not known by this Gmesh. So it is not there yet. If I want to have it here, I need to click on it and then say apply. Okay, if I say apply, what it does is it runs Gmesh again. It does the meshing again, but at the moment of meshing, because I have defined the mesh groups, it's also writing the info about the mesh groups as well. If I say okay, now you see it's not grayed out anymore. And that's an important indicator, because if I don't do it correctly, if it's grayed out, and if I export the mesh, then the exported mesh will not have these groups. Okay, in order to have the groups really in the mesh, I need to go in and say apply. I don't have to do it every single time. I can do all the groups and then in the end once say apply. Okay, so I'm selecting it again. I'm going to the mesh and choosing a mesh group. And now I want to have label, again label, but this time I want to choose some faces. So first of all, what I have in mind is like a beam bending. So I want to hold clamp here. Okay, so I'm choosing this one and adding it. It's not working. Why? Because first I need to choose add and then choose the surface. And if I do it correctly, first add and then the surface, then I see here it is written something, just an internal name, I don't care. So then I can say, okay, yeah, this is one mesh group, so I want to give it a name. Before I forget what I have chosen, I'm just giving a name. So this is the surface, which is I'm going to use as clamping, right? So I'm gonna hold it as enter. So now I'm going to do another mesh group. This is for the loading. So what I have in mind is like holding here and then putting a force on here. So I don't have to do that. Of course, I can put a force, for example, here, right? So depending on the application, what you want. So we can choose all surfaces. This is the nice part, of course, sophisticated geometry, and we can choose all surfaces. Again, I need to choose label. This is a face, and remember, first add and then choose the surface so we see it here correctly. Then I can say okay. And I'm gonna give it a name. So this is for loading, right? So I'm giving a name loading. So now, in order to apply these boundaries or groups into this mesh, so I need to double click on it and then apply. So before saying that, I'm gonna make a little bit nicer mesh. So I don't know exactly the dimensions, but maybe 3. Yeah, it's a bit better. So let's make it 2. So this is the element size. So if you actually go in, so this is like one element, roughly one element size is 2. That's the maximum element size. It starts here on the edges, put for each 2 millimeter a node. You don't see it, but actually here there's a node, and then starts triangulation, doing the meshing. So if I say I said apply, okay, now we can double check it is active. Okay. So now we're done. That's all we want to have for FEniCS. We want to have a mesh and we want to have the boundary conditions. So now I want to export it. If I select this one, I can go to File and Export. So here I'm choosing Export, and then for this 100,000 different possibilities, I'm choosing FEM mesh for FEniCS. You see, there are a lot of different possibilities. Freecad is really supporting a lot of different options, And also, since the version 19, this is the version 19 is the latest version which you can download, or you can also download the version 20 that I'm using here. I mean, version 20 is better for FEM meshing and so on. There are a lot of more robustness in meshing, so you can download the version 20. And FEM mesh for FEniCS is also inside. So I'm choosing this one, and it gives me automatically an XML. So, but here I want to use not XML, I want to use XDMF. Okay, so I'm just want to changing this to XDMF. The name is whatever you want, you can give it a name if you like. So I'm just leaving it here and say this is in my desktop Freecad path. Okay, so there's already one because I tried it before. So say yes. Okay, so now if I say export, it did not export yet. Okay, so now it is bringing me a dialog, so it's asking me a question actually. If I say okay, at the moment it will be exported. So before saying okay, I'm just looking what is this dialog saying to me. So there's an ID 012, this is just an internal ID, we don't care about that. These labels, this is what we have given, right? We have used here, loading for one surface, clamp for another surface, and body for the whole continuum body. And I can also see this is element type is face element, and this is an element which is a volume element. So then there's like for each, for example, for loading, not marked and marked. So if a surface element, let's go in and say, if this surface element, for example, here, this triangle, is not on the surface of loading, which is not right because the surface of loading is here. So that means this surface element is not on this surface. So it is not marked. So it is like having the value 0. So for this surface triangle, the value is 0 in this list, in this first list. But for the other one is also 0. For this one is also 0. For this one is also 0. But if I go to that one, this triangle has the volume 1 because it's marked, okay? So for all surface triangles which are on the surface, which is the loading, then they have the value 1. All the rest has the value 0. I can choose something else. I can choose 5 if you like. Okay, so that's an integer that I can choose whatever I want. So I'm choosing 1. Okay, so that's the same for clamp and that's the same for body. Okay, so now we have exported the stuff. I can have a look here. I have some other files, but here is exported unnamed FEM mesh, right? So now I'm going to open the FEniCS. So let me do the export again because I want to see the dialog. So I'm gonna say export. I'm gonna just write it on top of it. Say yes, and here's the dialog. So now I'm opening the FEniCS. This is the code that we had before, right? So now I'm doing some small changes in the code that we had before. We were using box mesh, so that was already we were generating a box. So now we are going to import the Freecad. In order to do so, I need to say where's the file. So I'm using this kind of a notation in order to say where's the file. So there's a path. Okay, so of course in your case the path is different than mine, right? Because now this is showing to my home, Mac, desktop, and so on. In your case, maybe you are using Docker and the shared directory, so you had the same path. So the Freecad file is somewhere, and then this XDMF file is somewhere, and this one is somewhere else. But maybe you just put them all together, so you don't need this mesh path, right? So if this is the case, then you're gonna say, yeah, I don't have the mesh path, so I can do this. So then they are going to be in the same directory. In my case, I have something somewhere else, right? This FEniCS file is somewhere else than that one. This is why I'm using here. And here on this mesh file, that's the name. That's the generic name that I may choose whatever I want. I just said, okay, this is why I have this funny name. And XDMF is the file type. So now I'm creating a mesh. This is the function which is coming from the Dolphin import all. Okay, that's the stuff. And now I'm using XDMF file. This is again another function which is coming from Dolphin import all. And then while I have opened this mesh file, so that's the name of the file. Read it. I'm saying read it means like nodes and all the stuff is inside. Maybe let me open that once that you see how it looks like. This is a simple ASCII file, so there's no binary or something like that. So if I go on top, then you will see what it is. It is something, I don't have to look at it, right? So I'm just opening it in order to give you an impression of what it is. So it is a simple file which is actually saying the base mesh. So the topology is tetrahedron. Tetrahedron is like having 4 nodes connected in 3-dimensional space, and these are the 4 nodes. That's the first element has the node number 4232 and so on. Okay, these 4 nodes have some IDs, and you can say, okay, but where is this 4232? This is, if I scroll down a lot, I have a lot of elements here. Here I have all the coordinates of these nodes. For example, if I can go to the beginning, I couldn't go, it's difficult. I go to the beginning. Where is this? Should be here. Interesting. Okay, here's it. So at the beginning is here. So it's starting like XYZ. That means all the coordinates of the nodes. And the nodes are like the first, that's the first node. Node ID 1. There's here somewhere node ID 1, I don't know where. So node ID 2 has these coordinates. Node ID 3 has these coordinates. It's just in a way explaining like the nodes, the coordinates, and the nodes, the 4 nodes connecting together as an element. And then later on, after telling all these, this is the mesh, okay? After all these, I have a bunch of 0. You remember we were talking about the surfaces or solid or so on. So like it is 0 or 1. It's unmarked or marked. So this is bunch of zeros and bunch of ones. And this is again in the order of the IDs. So that means if I say read mesh, what it does is it goes to the designated sections and then read the coordinates of the nodes and also the connectivity. That means which nodes are building an element. And this is all the information what FEniCS needs for making a computation. This is the mesh. Alright, so it is constructing the mesh here by reading it, and then I have the mesh. Of course, I can ask what is the dimension. Obviously, it's going to be 3 because it's 3-dimensional, right? So dim dimension is 3. So now I'm using this number and creating a mesh value collection. So these are the values 0 or 1, marked or unmarked. And then I'm just giving it a name and then using into this cells just a name, putting it the zeros and ones which are indicated by body. Body is a name or label that I have given. So you can see it on the dialog here. So we have loading, clamp, and body. Body is for the volume. Volume means 3-dimensional. That means the dimension is 3. If I do the same, exactly the same here, but this time for loading, see, that's the loading. This is a face. This is a surface element. I mean, surface element is 2-dimensional. That means 3 dimensions minus 1. So that's what I'm doing here. So dimension is 3 and minus 1 is a face element or surface element. They call it facet. So this word doesn't exist in English. So face is 2-dimensional, an edge is 1-dimensional. So if you have a 3-dimensional continuum, then the surface is 2-dimensional. But if you have 2-dimensional continuum, the surface is an edge. So it's not anymore a face. So instead of that, they have created something like facet, a new word, if you like, which means like face or edge, depending on if you're calculating 3-dimensional or 2-dimensional. But whatever it is, it's always 1 dimension less. So that's why I'm using here. So dimension is 3 in my case. So 1 dimension less is a surface element which has the jargon facet. It's a FEniCS specific jargon. Now I'm using it here and saying read whenever you see something in the section which means or which has the label loading. So this is what I have chosen here. I could give another name, I have to put it here. And I am creating a list, which is loading list. Now I'm doing exactly the same. I'm creating another list, clamp list. So it doesn't matter, I'm just using here faces, just a temporary while. So I'm using it here, but then later on the loading list is the most important stuff. So this is why I'm just using the same name again. Doesn't matter, I'm just overriding it, but at the end, loading list and clamp list. These are the two lists for these two different 0 or 1 for the clamp ones, or 0 or 1 for the loading one. These are going to be used. So now the rest is more or less the same that we had before. So I'm creating a vector function space for the displacement. I'm using here SAS and I don't need that, by the way, so I can just delete them. So that was necessary beforehand because we were not choosing by using mouse. We were just choosing by geometric explanation where is what and so on. This is why I don't need that. What I do here now from FreeCAD, I already have these lists, right? 3 different lists. Now I'm using the list for loading here, and I'm saying, but not everything, just take it if the subdomain ID is 1. So why it is 1? Because we have used 1 for marking. So if you don't like to have 1, you can of course say, no, for loading I'm gonna put here 5. Okay, so or 7. Any integer that you like. You can also put 324, but then you have to put here on the subdomain ID also 324. Okay, that's this number which is matching in this list, a loading list, which is coming from this dialog loading 1. And this is the dA, which is the surface integral measure that I'm going to use in the weak formulation, which is right here. So this is for this traction. The traction is the force per area applied on the surface. So this traction is, technically speaking, a force per area. So I'm giving the force here 100 Newton, and I had no idea about the area. So of course I can go to FreeCAD, measure it, and say, that's a rectangular area, so I can find out the area. But if the area is more complicated, it's useless. What I'm doing here is now I'm using an assemble. Assemble means take the integral. So I'm taking the integral 1 times this surface. So which is nothing else than the surface. How big is the surface? The surface area. So this surface area I'm calculating in FEniCS and then dividing the force by this area. So I'm also printing it out in order to see, have a feeling of how many square millimeters is that. And I'm applying it as the traction. So the traction has the unit Pascal, or here I'm using Newton and millimeter, that means megapascal. And this traction has the unit megapascal is a vector 0, 0 in the z direction, F divided by area. So let me go back here so we see the XYZ. This beam has a bending or deflection along z because I'm going to put a force which is along z. If I don't want to have that, if I want to put a force on the same surface but in the other direction, of course I need to change it here. Okay, this is a vector 0, 0 F divided by area. So I'm using again trial and test functions. U is for displacement, delta U is the test function, and Young's modulus and Poisson ratio, these are the material quantity, material parameters. I'm choosing here 70 gigapascal or 70,000 megapascal, which is more or less typical for aluminum alloys or magnesium alloys. And for the Poisson ratio, I'm taking 0.3. So the rest is more or less the same. Here's the strain, and here's the shear modulus, Lamé coefficients, and that's the Cauchy stress. So that's the stress tensor that I'm putting it here, an isotropic material, and here's the equation that I'm solving. So now I'm creating a displacement vector, solving it, and then saving it as displacement vector and writing it out in PVD file type. This is, if you remember, we have used that. We have used VTK, PVD and VTK. Both of them are used for paraview. So this is technically, I am pushing the displacement into the paraview, and before that I'm solving it, and once I'm solving it, I'm using solver parameters. So this is one of the good parts that I'm using FEniCS, because if I want to do parallel computing, I can do it. If I want to do different solvers, I can choose it. If I want to do some more sophisticated stress functions, I can just put it in. Okay, and the whole code, if the geometry is not changing, even not changing the FreeCAD, I can do whatever I want because I have the full control here. So now I'm saving it and now starting it. So I'm gonna use FreeCAD. Is this like correct position? I need to go to this desktop, right? So it's in the desktop, home, desktop, and FreeCAD path. And by the way, I'm using here Visual Studio. Of course, there are other possibilities. I can also try to get here. There's a really nice possibility to, I don't know how to do that. Like I can copy, maybe right click. Yes, I can do the right click here and copy path. Okay, so I can use the cd change directory and go to this path automatically, right? So I need to delete this one. So what is to say? Now I'm going to run Python FreeCAD, and let's see what's gonna happen. So this is the print. This is the print. So it's finished. This is the print that we have used here after creating an integral of area. That's the surface area and print area. So that's this one. And then it has solved. Nothing happened, of course, because we didn't say print anything. What we have said is actually just save the displacement as results PVD. So in order to open that, I need to open the ParaView. So let me see first. It's, yeah, this is the correct one. That's the correct one. So I can now put it in and say apply. Now we opened in ParaView. Okay, so that's the result. And the result looks fairly nice. So we can try to make it even looking more nice. So I'm going to use the same techniques that we used before. I'm going to use warp in order to show it nicer. So now I'm going to say apply. So that's the displacement. Even we could see some displacements. Actually not a small displacement at all. I didn't know the force that I need to put. I just put something. I'm gonna make it a bit larger. And here for better visualization, I'm showing also the one before deformation. So we can see here before deformation and after deformation. So it looks cool. I can also change the, of course, colors. I can change it here. I can choose some other colors, more pronounced one maybe, why not? And also here I can choose on the top, I can choose the name of the legend, so I can just give it a better name, displacement I can call, or I can even use this kind of stuff in order to make it a vector. Okay, so it's like a mathematical way of writing it. And if I want, I can make it even larger here. So okay, and if I like it, I can go to file and save screenshot and produce a PNG file in order to use in the report. So what we have seen is now a combination of FreeCAD and FEniCS. Do we really have to use it? No, I mean, you can also use Calculix, right? So there are like different options for the elastostatics. For the simple case that we want to do, both of them are equivalent. I'm not gonna say one is like way better than the other one. But if you want to do a generalization, and if you want to have the full control and knowledge of what's going on behind, FEniCS has some advantages.